Hi, I'm Carlton Coffran.
And I'm Linda Roald, and we are here to talk about convex relaxations in power system optimization. In this presentation, we will talk about the AC power flow equations and where they come from. Okay, so I will start out and just kind of recap a few preliminaries about power in alternating current systems. So what we are talking about here are three-phase symmetric power systems, and for those of you who are power engineers, you should know that these are the systems that can be transformed into a single-phase equivalent. So we have active power, which are denoted by lowercase p, reactive power denoted by lowercase q. We have the complex voltage by capital V, and the complex current by capital I. From these definitions, we can define the complex power either in terms of active and reactive power, or in terms of the product between the voltage and the complex conjugate of the current. A couple of more definitions on the apparent power, which is the magnitude of the complex power, and also we could talk about power factor, which is the active power divided by apparent power. These two definitions will not be super important for these presentations, but I wanted to include them here. Okay, so based on these, I will go ahead and talk a little bit about what is a power network. And when I'm going through these definitions, they will be in more of a graph representation type language. And this is because we want to get all the computer scientists on board with what this is. And for the power engineers, this is probably going to be a recap, mostly anyways. So in the power network, we have a set of nodes, or so-called buses, that represent physically substations and connections inside of the grid. On some of those nodes, there are sinks, or so-called demands, which are withdrawing power from the node. And here you should remember that each of these sinks are given as a complex power, which consists of an active power consumption and a reactive power consumption. Additionally, on some of the nodes, we have sources, which represent generators, that are injecting power into the node at various locations. Between the different nodes, we have edges, or so-called power lines, that are denoted here by E. And each of those power lines have an admittance which represents how easy it is to transport power from one node to another over a given edge. So this is the system, and I'm going to now talk a little bit more details about what is a power line. So a power line really connects two nodes in the network. So here you see a power line connecting node I to node J, and in the middle there is the series impedance Yij. Yij is given as 1 over the impedance, where R represents the resistance and X represents the reactance. And this is really the simplest model we can have of a power line. To represent the current that is flowing over this line, which is given by Ij, we are using Ohm's law. So this is the physical law that describes the current, and it is given by the admittance times the voltage difference between node I and node J, and that gives us the current flowing from node I to node J. So note here that if you have a high voltage at node I, power will be flowing from I to J. Current will be flowing from I to J. If you have a high voltage at node J, the current would actually flow in the other direction. The power flowing across this line, and in particular from a node I into the line, is given by Sij, and is the voltage at node I times the current Iij, and is given and can be shown as this expression down here. We should note that we have a different expression actually for the power flowing from node J into the line, which is given by the voltage at node J times the current, the complex conjugate of the current Iij. And in general, those two are not the same because we have power losses that are occurring on the line.
I think it's also interesting to note here that you actually need to measure either the current or the power on like say, the I side of the line or the J side of the line. In a lot of CS applications, you just need one, say, variable to represent the flow on the line. But in power systems, there really is a difference between what's happening very close to one bus versus the other.
Yeah, so it is important to take this into account. Okay, so this was, as we said here, the simplest model is really of a series impedance of the line. We can have a more realistic model, particularly if you have long power lines. It is important to take into account what is called line charging, which is done by using this more realistic model called the pi model. And the reason we call it the pi model is really because it looks a little bit like a pie. I mean, there's two lines that are vertical connected by this horizontal line at the top.
The Greek letter pi.
The Greek letter pi, yeah.
Not like a pie.
Not like a pie. So these are called the shunt elements. And the way they enter into Ohm's law are shown down here. So essentially we are just adding Yijc times the voltage at node I on one end, and now we see also Yijc times the voltage Vj at the other end. And what we see here now is actually that the current might be different at the different nodes flowing into the line, and that's because it might flow through the shunt elements to ground. We can also kind of regroup this a little bit, and we can formulate the power flow the way you see it here. So here we have the expression for Sij and Sji on the different ends of the line respectively. So it sort of still looks very similar. They are still not the same, but yeah, we now have these shunt elements in there. An even more realistic model of a power line is a line that can include a transformer. So this is often called a branch rather than a power line. And this transformer represents a change in the voltage from on one side of the transformer to the other side of the transformer. And this is used to, bring the voltage from a high voltage down to a lower voltage, or the other way around, as power is being injected from one voltage level to the next. And when we put that transformer into the power flow equations, we use this Tij to represent the ratio between the voltage on one side of the transformer to the other side of the transformer. So this is called the tap ratio of the transformer. And really it enters into the power flow equations as you see down here. And I'm not going to go into more details about transformers. There are many things you could say about them. For example, they can both they might not only transform the voltage magnitude, but they can also transform the phase of the voltage, but we will not go into these details here. Okay, so if we look at to summarize, there are different power flow formulations. So we can then have a simple series admittance, we can have the pi model, or we can have a pi model with transformer. So in the following, we are mostly going to use this notation for the simple series admittance in our presentations. And what we are going to see is that when we are doing optimization, and if we assume that Yij and the shunt elements and the transform tap ratios are constants in our formulation, then all of those formulations are very similar for optimization use. They can be different in practice, and these are important aspects of modeling, but since we are really wanting to focus on optimization here, we are going to stay with the simplest model of them. Okay, one last thing about power flow equations. I also wanted to touch on the polar form of the power flow equations. So if you take the definition of complex power and you take the definition of the line admittance, and you use this the definition of the voltage product, so the voltage on node I times the complex conjugate of the voltage on node J, you multiply these things and you split it into the real and the imaginary part of the equations, you will get the polar form of the power flow equations, where we have the active power Pij and the reactive power Qij represented in the equations that you see down here, where they are expressed in terms of the voltage magnitude and the phase angles at each node of the system. So this is a very commonly used representation of the power flow equations that can give a lot of interesting intuition, but for the presentations we are giving here, we are mostly going to stay with using the complex numbers directly, as you see in the upper part of this slide.
Yeah, so I think one thing that is interesting is you have a lot of choices for how to represent complex numbers when you're going to do an optimization algorithm or solve a system of equations. You can put them in rectangular form or polar form as you like. And what's interesting about these presentations is we can give you a lot of the intuitions for these systems and the mathematics just in the complex numbers. So we don't have to get into the details of a real number representation or how you implement those for most of the presentations.
We should maybe mention that as we are getting closer to talking about relaxations, for many of the relaxation, it is important what type of form you use. Is that correct to say?
Yeah, many of the relaxations are inspired by different types of variable spaces, but you can link them together, and yeah, there are many choices.
Yes.
So I will continue by talking a little bit about how you combine these power lines into the physics of the whole network system. So we have transmission lines in our network, as we saw before, and we have the admittance data. And now, by using Ohm's law and the definition of power, we have this equality constraint, which tells us how the power is defined on Sij for every one of these edges in the power network. We also have another constraint, which just comes from the fact that current should be conserved in every node in the power network. So basically, when you have all the different powers entering a bus in the network, it should all balance out. So what you can see here is that you have some generation, SG, you subtract out the demand at that local node, SD, and then you have the flow of power on all the lines that neighbor that bus, Sij, and all of these should be equal, so everything is balanced out. And so this comes from Kirchhoff's current law. Conservation of flow is a very natural analog from computer science, and this is the other core equation for power flow in networks. So now we can put all this together and we can state what would be a power flow problem in terms of the system of equations. So our unknown variables are going to be the voltages at every bus in the network, and then we're going to have these two constraints for each node in the network and then for each edge in the network. Now, it's worthwhile to note that these are equality constraints, so you can do a substitution, and sometimes you'll see them combined into a uniform constraint like this, which is equivalent, but now you don't have an explicit variable for each flow on the edges in the network. You've just incorporated that into the balance equation. Now, another concept which comes up frequently is this idea of a admittance matrix, which basically refers to the fact that you can use the summation, which you see in the middle here, to group a bunch of admittances together for every voltage VII or VJJ and VIJ combination, and you can make a big matrix out of that. And then you can think about solving kind of a system where you have this matrix of admittance and then the deltas of power injections at all the buses, and then you're just looking for what the voltage values are. It's worthwhile to note that this is a very stylized version of an AC power network. So in practice, you would need to define things like a slack bus, PV buses, PQ buses, and kind of set up a power flow study. We're not going to go into the details of how you do that here because we're going to jump directly to AC optimal power flow where that isn't necessary. So we're just right now going to skip ahead, and if you're interested, read a power system textbook on how you can formulate a proper power flow problem. So those equations are all nice, but they don't really give you a lot of intuition for how these systems behave in practice. So what we'd like to do now is give you two intuitions for different properties that kind of arise out of the equations as you've seen them. And the first one has to do with line losses in the network, and the second one has to do with the implications of Ohm's law for the whole network system. So let's start with line losses. So I'm going to use as a kind of an intuitive test case a very simplistic power network where we just have one voltage, one generator bus, one load bus, a voltage at each side. We have the current and the power on each side of this very simple line. And then let's just develop some of the basic physics equations. So we have our current equation that comes from Ohm's law, and then we have the current equation for the other side of the line. And what you can see here is because the only difference in these two is the inversion of Vi and Vj, that Vij is equal to minus Vji. Move it over, and now you can see that these sum up to 0, which implies that no current is lost as it flows across this line. Now, a natural question is, well, what happens to the power when you add them up like this? Is there no power lost across the line? Is there a power lost? What expression does it have? So let's develop that. So we have the definition of Sij and Sji, and as Line mentioned, this is a very simple stylized model. You could do the same type of derivation for the more complex models. Then you add them up like this, and now you can collect all these V terms. And initially, this may not give you much of an insight as to what's going on. The key observation to make is that you can actually factor these two expressions to Vi minus Vj times Vi minus Vj conjugate and apply the definition of an absolute square. So now we start to get some interesting intuitions for what's going on when you add the value of power at either side of the line. So the first thing you can observe is that the absolute square here, Vi minus Vj, has to be a positive number. So that's always a positive quantity. And in typical operation procedures, Y conjugate will be positive. So usually the G component, which is the conductance, is a positive value, and then the susceptance will be a negative value usually, and you take the conjugate and that turns the susceptance into a positive value. So from that you can deduce this kind of valid inequality, which says that when you sum up Si and Sj, both in the real and imaginary part, you would expect that you won't, you can only lose power on the line. So this value can only be greater than 0. But
so yeah, so kind of an implication here, an important implication is that active power will always be lost on the line. There can, so as Colin has said, in most typical transmission lines, we can only lose power on the lines. It is possible on certain types of edges in a network. For example, if we have cables, we could actually have generation of reactive power on the line. That is not covered by this model that we are showing here because we don't have any shunt elements. But there could be cases, just to mention that, where reactive power will actually be generated on the line rather than be lost. But active power should always be lost on the line. Otherwise, your model might be doing something strange, or you should maybe check that the numbers you have are the right ones.
And I think as well, this kind of approach is a good way if you have a more general model that, say, incorporates cables, you can use this kind of approach to get an intuition for what might happen as power flows across the line.
Yeah, definitely.
The next intuition about losses has to do with the fact that they're quadratic in the amount of current that's flowing across the line. So to do that, we'll start with this kind of factored derivation we had before, and we'll go back to our definition of current from Ohm's law. Now, if you factor that definition in terms of Vi minus Vj and then substitute it in, you see you get an expression like this one, where you have the absolute square of the current divided by Y. And if you apply that absolute square and cancel the terms, what you'll see is that you have the impedance, Z, times the absolute square of current. And this is very interesting because now we have one variable, the absolute square of current, and we can see how the line losses are impacted by that variable. And so here's a picture for that absolute square of current and how it depends on both the real and the imaginary component of that quantity. And what you can see here is it's a cone, and we have an equality constraint, which means we have to be exactly on the surface of this cone and not inside or outside of it. And you can already see some non-convexities of this problem cropping up just from this very simple equation. The other intuition we can give you has to do with Ohm's law. So it's important to note that these power flow equations are nonlinear. They can have multiple solutions, they can have no solution. It's extremely hard to characterize their behavior in general. But what we'll try to do is give you an intuition of what this constraint means in aggregate in a very stylized way. So imagine you have this stylized power network where you have a generator at the top and one load at the bottom, and then all the edges or lines in the network have equal resistance. Now these should be complex resistances if we're an AC network, but this is just a stylized example. What you expect is that if all the resistances are the same, the power has to flow in equal parts on each side of this path to the demand. And this is just an aggregate consequence of Ohm's law. And then if you had a situation more like this one, where there was an imbalance in the resistance on the different paths to the load, the power would split proportionally to the relative resistance of those two different paths. So when you apply this Ohm's law in the cycles in the network, you start to get these type of properties, although it's quite hard to show analytically.
Yeah, and it's maybe also worthwhile to note here that in the power networks, it is typically so that we have very little ability to control how those powers are flowing. So the admittances of the lines or the resistances that are shown here, they are typically fixed and we cannot really control how large they are. So therefore, power is kind of just flowing the way the physics of the grid are determining them. And our main way of controlling the flow of power is really by controlling the injections or the consumption of power. So that is a relatively limited amount of control relative to many other types of networks where you might be able to control specifically the flow over a certain edge. I wanted also maybe here to make one more comment about the multiple solutions of the power flow equations.
Mm-hmm.
So as or actually the no solutions of the power flow equations. So when we are specifying this problem, we typically specify the power injection on the node. That is usually the variable that we are able to control or that is given to us. And for a certain set of power injections or power consumptions, there might be no set of voltages that actually that give us these power injections. Usually, if we do have voltages specified, we should be able to find power injections that correspond to them, but those power injections might not be the ones that we want.
Right.
Yeah.
So to recap, in these lectures, we've developed the physics of power systems, and then we've used those to derive the AC power flow equations. And we provide you a couple of intuitions for how power losses work on lines, and also how Ohm's law can work to split power and kind of force the power down certain paths in a network.
And for our next lecture, what we are going to do there is that we are going to sort of expand on the typical operating constraints of power systems. So look into like what happens when we are not able to really operate the system without any constraints on the power injections or on the voltages. And from that, we are then going to develop the AC optimal power flow problem, which are taking those operating constraints into account in order to find the best operating point for the system.
So we'll be generalizing the power flow, basic power flow problem into an optimization problem by adding inequalities and other types of constraints.
Yes.